Hello everyone, welcome again. Here is an interesting question on the board. If you wish, you may pause here and you can type your answer in the comment box. To elaborate this question, I am performing a demonstration in front of you. So, here we have an empty glass, here we have an empty ice cube tray and some water. What I'll be doing, I'll pour some amount of water in the glass and then I'll put the same water in the ice cube tray. Later on, I'll be putting this ice cube tray in the refrigerator to form the ice cubes. And then I'll grab the ice cubes from the refrigerator. I'll put the ice cube in the glass and will observe what happens to the water level as the ice melts. Got the question? Think about it. It's a nice question. And then please post your opinion in the comment box. I'm just going to the refrigerator to put it there, and then after some time I'll be grabbing the ice cubes to drop into the water. See you again. So here I have the ice cube from the refrigerator. I'm dropping it into the water and then I'm marking the water level using the marker. Just pay attention. Here I'm going to mark the level of the water in front of you. This red color might be you can see, or I'll drop the blue somewhere here. If you require, I'll drop the black color also on the glass somewhere here. I hope it's clearly visible to you. The ice piece is floating in the water and we have marked the level of the water. We are going to observe what happens to the water level as the ice melts. I hope till now you have made up your mind and you have posted the opinion, which is the water level will remain same. I'm going to explain that over the board. Just pay attention. We are considering the case 1 when the ice floats. If the ice is floating, it means that its mg is balanced by the buoyant force. For that, let me draw a diagram. Suppose this was the initial water level in the glass before dropping the ice. Water has the density rho water. Then we drop the ice cube. So ice cube covers up some space like this. Do you agree? And moment we drop the ice cube, some water from this part will go up here. So that I am showing like this. Let's say the water reaches here. So this is the water level, this. Now the ice cube is continuously melting and we have to check what happens to the water level. The concept is simple. What we'll be doing, we'll find that this floating ice cube displaces what amount of the water, what volume of the water. And then as the ice cube melts completely, it will form some water. If that water formed is equal to this volume displaced of the water, then water level will remain same. By melting ice, if the volume of the water formed is more than the initial volume occupied by the ice inside the water, then water level will rise. And if by the melting ice, the volume of the water formed is less than this initial volume occupied inside the water, then the water level will decrease. Got the concept? So let's start the calculation. Initially, since the ice cube is floating, so we can write that mg of the ice cube is balanced by the buoyant force. According to the Archimedes principle, the buoyant force for a floating object is equal to the weight of the fluid displaced. I hope you remember that principle. So I'm going to write the weight of the fluid displaced by the floating ice. The ice is displacing some weight of the water So we can write that volume displaced of the water multiplied with the density of water into G. The ice is also displacing some weight of the air here. Here are the air molecules that we should write as volume displaced of the air into density of air into G. And here is the mg. If we check the numbers here, the density of water is 1000 kg per meter cube, while as the density of air is 1.2 kg per meter cube. It means this number is pretty small as compared to the number here. So we are going to neglect it. Now the G is getting cancelled out. So we have the volume displaced of the water is equal to mass of the ice divided by the density of the water. Simple and easy case. Now case 2. When the ice melts completely, then we know that m gram of the ice will form m gram of water. So we can find the volume of the water formed. VFW will be equal to the mass of the water, which will be equal to the mass of the ice divided by the density of water. Pretty interesting conclusion. The volume displaced by the water is equal to the volume formed of the water by the melting ice. Hence, the water level will remain same. I am explaining this here. This was the volume displaced of the water. This much was the volume displaced of the water by the floating ice. And the same volume is being formed by the melting ice. So this gap will be filled exactly by the melting ice, means the water level will remain same. And I hope you can observe it on this glass also. Can you check what is happening to the water level? It stayed the same. The entire ice melted and we can see the same water level in the glass. So it's pretty interesting demonstration. If you wish, you may try this at your home. You may note it down, and based on this, I'll be bringing up two more interesting questions. So here is another interesting question based on the same format. Would you like to post your opinion in the comment box? I'm waiting for that, and then we'll be simplifying as usual the things on the board. I hope you got the correct answer, which is the water level stays same. Let's see the simple explanation here. Suppose this is the container and this was the water inside the container. The density of water we consider as rho W. Then we drop the ice cube here. So the ice cube appears like this. Ice cube occupies this much volume of the water. So that amount of water finally comes here. Got it? According to the question, this time the ice has the air pocket inside it. Archimedes' principle says that a floating object displaces the weight of the fluid equal to its own weight. It means the buoyant force and this weight of the ice cube are getting balanced. So I am writing that here as the case 1. When ice floats, the buoyant force should be equal to the weight of the ice. The buoyant force will be equal to the weight of the fluid displaced. So the ice is displacing this much weight of the water. Do you agree? I am writing that here. Weight of the water displaced will be equal to the volume displaced of the water into density of water into G. As well as this ice is displacing some amount of air also. So that weight of the air we should write the volume displaced of the air, density of air into G. And the weight of the ice I'll write the mass of the ice plus mass of the air inside it into G. Got it? M ice indicates the mass of the ice and M air indicates the mass of the air inside the air pocket. Okay. Now, we know one thing, that if we compare this data and this data, here rho W is density of the water is 1000 and here density of air is 1.2 kg per meter cube. So we are going to neglect this term. Same we can do here. If we compare the mass of the ice and the mass of the air pocket inside the ice, then this mass of the air pocket, air bubble, is negligible. You get it? The G gets cancelled out. So we have the volume displaced of the water by the floating ice is equal to the mass of ice divided by rho water. Pretty clear? Now, the entire ice melts, that we consider as case 2. When the ice melts completely, the m gram of the melting ice will form m gram of the water. So we can easily find the volume of the water formed is equal to mass of the ice divided by rho water. Again, the interesting result. Volume displaced by the water is equal to the volume of the water formed. And since the volume displaced of the water and the volume of the water formed are equal, so by melting ice, this much gap will be occupied inside the water. Hence, the water level stays same. Got it? Or logically also, you can deduce the answer. When the ice will be melting, the air bubbles will escape out and the weight of the air bubbles, the mass of the air trapped inside the ice, is actually negligible as compared to the mass of the ice. So the answer is equivalent to the previous case, the previous question. I hope you enjoyed it. You may note it down. Here is the last question for you. I again request, pause the video here and please post your opinion in the comment box. I hope you got the correct answer, which is the water level decreases. Let's see the explanation here. Suppose this is the beaker containing some amount of water. Water has the density rho water. Later on, we drop the ice cube here, and this time the ice cube has a heavy iron ball inside it. When we drop the ice cube here, it displaces this much amount of water, so that water will appear here. Got it? So here is the initial water level. Now we start the solution of the question. Since the ice cube is floating, so as usual, the weight of this ice cube is balanced by the buoyant force. I am writing that part here. The weight of the ice block is equal to mass of ice into G plus mass of iron ball into G. And the buoyant force will be equal to the weight of the fluid displaced. Since this object is floating, and according to Archimedes principle, we have seen many times, the floating objects displaces the weight of the fluid equal to their own weight. So weight of the fluid displaced means I should first write the weight of this water which was displaced by the ice cube. Weight of the displaced water will be the volume of the displaced water, density of the water into G. As well as the ice is displacing here some amount of air also. So volume displaced of the air into density of the air into G. We know that density of air is 1.2 kg per meter cube, density of water is 1000 kg per meter cube. It means we can neglect this term. It's going to be pretty small. Now the G gets cancelled out in the entire computation. So here we have the volume displaced of the water is equal to mass of ice divided by density of water plus mass of the iron ball divided by the density of water. Got it? Now, proceeding further, case 2. When the ice melts completely, if the m gram of the ice melts, then it will form how much amount of the water? M gram of the water. So, I am writing that here. Volume of the water formed, which we indicate as VFW. Volume formed of the water is equal to mass of the ice divided by rho water. M gram of ice will form m gram of water, and the volume of the m gram of the water will be m divided by rho water. When the ice melts, this iron ball sinks, and according to the Archimedes principle, if some object sinks in a fluid, then it displaces the volume of the fluid equal to its own volume. So here is the volume of the water displaced by the iron ball. Got it? You can relate it with an example. Suppose there is a swimmer. If the swimmer is swimming, floating, then it displaces what amount of water? Correct. Equal to its own weight or more than its own weight. Got it? Now suppose there is someone who doesn't know the swimming and that person sinks down in the pool. Then that person displaces what volume of the water? Equal to his own volume. Got it? So the sinking iron ball will displace the volume of the water equal to its own volume. Clear to you? Now, if we check this data and this data, we'll find the result, we'll find the answer. I'm going to compare the data. Let's check it very carefully. VDW, the volume of the water displaced initially, is actually greater as compared to VFW plus VDI. The density of iron is in between 7,000 to 8,000 kg per meter cube. So this data will be smaller. If this data is smaller, then we'll get such a result. And this result indicates that initially the volume displaced of the water was greater and later on it is less. So the water level will fall down. Got it? I hope you understood the concept. You may note it down and then I'll be putting one similar question for your practice. Stay awesome. See you again.